Good evening, Southport Scientific. Two short talks, both on the theme of exploring the solar system. Don't worry about the numbering. This one happens to be part 4. Don't worry, you don't need to know about the previous 3 parts for this, hopefully, to make sense. So I'm talking about exoplanets, planets around other stars. And we can ask, why bother looking for exoplanets? How do we actually go about finding planets around other stars? And how do we go about looking for life? And I'll be asking the question, what's the next step in that direction? So we can ask, why bother looking for exoplanets? Well, it's essentially scientific curiosity about what the rest of our galaxy is like, but also it's hopefully telling us something a little bit about our own solar system. Are there other planets out there in any way similar to the planets we have within our own solar system? Are there any planets like Earth, for instance? And ultimately, we'd like to know, is there life anywhere else in the galaxy? We haven't finished exploring the solar system itself yet. We may yet find life elsewhere other than on Earth, but we'd also be interested to know whether there's life on exoplanets around other star systems. But ultimately, even if there isn't, exploring and understanding how other solar systems exist, how other exoplanets orbit around other stars, will hopefully give us some inkling as to how our own solar system works. So in terms of how do we go about finding planets around other stars, there are a number of different methods. So I'm not going to go into any detail on all of these. There are 5 principal methods. The first one, called radial velocity, is looking at the velocity of stars, and effectively it's looking for wobble. In other words, if a planet is going around a star, then that star will be perturbed slightly by the orbiting planet, and so the star will be coming towards us or away from us, and that can give a wobble in the star, which can be picked up by looking at the spectrum of the star. Second technique is a transit technique. If a planet happens to move in front of a star, it can block some of the star's light. And so if we monitor the brightness of a star and see it dip, that could be a sign that a planet has moved in front of the star. So we're looking for shadows. We're looking at the intensities of stars to see if they drop. The third technique, which I'm going to talk about, is direct imaging. And that means if you have the right sort of setup, if you look at a very distant star, which of course is very bright compared to a planet, if it's possible to block out the light from the star, then maybe you'll see a faint planet next to it. That needs a very accurate blocking of the starlight, and I'll come back to how that's done a little later. But given that a star might be 1,000,000 times brighter than a planet, it's effectively impossible to image it directly unless you block out the starlight, and then hopefully you'll see the faint planet light next to it. There's a couple of other techniques which haven't found that many exoplanets, so I'm not going to talk about them in any detail, but they are mentioned in the handout if anybody wants to pick that up at the end of the talk. So firstly, method number 1, the idea of radial velocity. If we have a planet orbiting a star, then the star is going to move slightly backwards and forwards, because a planet doesn't orbit a star. The planet and the star orbit around their common center of gravity. Now that might be very close to the star, depending on how big the planet is, but if a planet has a mass, then it will make the star wobble. And the indication at the bottom there is the light from the star will be pushed slightly towards the blue or slightly towards the red, depending on whether the star is coming towards us or moving away from us. A slightly more accurate way of thinking about the spectrum of the star in this cartoon, that's what a planet orbiting a star would look like from above. That's what it might look like from the side. But what would it do to the spectrum of the star? Well, that's shown in the bottom right-hand corner here. If we look at the characteristic lines that are in the spectrum of a star, when we take the starlight, put it through a prism or a diffraction grating to split it into its colors, we can see the characteristic features of the spectrum get moved a little bit towards the red or a little bit towards the blue as the star is moving away from us or towards us. So if a planet is orbiting and the star is wobbling, then the characteristic elements of the spectrum will go backwards and forwards and backwards and forwards. So that's a signature, if you like, of something orbiting a star. We don't have to be able to see the planet. All we need to do is pick up the starlight, split it into colors, and then we can see what's going on. Second method. If we've got a solar system edge on, then it's possible that the planet will move in front of the disk of the distant star and block some of the starlight. The amount of starlight that's blocked will depend on how big the planet is, not in terms of its mass. In the previous technique, the mass of the planet will determine how much the star wobbles. In this case, it's the physical size, the diameter of the planet, that will determine how much of the light from the star is changed. And we can see here an indication of what we might pick up. The starlight, which would effectively be constant for most of the time, will dip when a planet moves in front of the disk. And if we have two hypothetical situations, a large planet on the left and a smaller planet on the right, then the amount of light that's blocked by the larger planet will be larger, and so the dip is deeper. So by looking at starlight, again, we don't need to see the planet, we just look at the starlight, and then if we see the depth of the dip, that tells us about the size of the planet compared to the size of the star. So if we understand enough about what the star is, we can tell something about what the planet is in terms of its relative size. And that not only works for individual planets, it works for entire solar systems. So here we have a hypothetical situation of 3 planets going around a star. There's one planet that's already been through, producing a dip. And there's a second planet coming in, and then the third one before the second one is done. So you get a very complicated change in the brightness of the star. But as long as you carefully monitor what the brightness is, even if there's lots of planets going around the star, it is possible to figure out how many planets there are and how big they must be in order to produce the particular so-called light curve, the dips that we see characteristically in the bottom left here. So this is, again, a different way of looking at it. This is what we might expect to get ideally. What we actually do is measure the brightness of the star again and again and again and again. These are the blue dots. And when we've got a whole load of dots, we then say, what's the best fit, i.e. what's the white line that gives us the best fit to what's going on. And that gives us then the properties of the planet that's going around this particular star. If we have a look at actual data rather than just cartoons, here's data taken from the James Webb Space Telescope. So again, it's staring at a star and the starlight is effectively constant and then goes through a dip and then recovers back to its original value. You can't read the scale probably, but that's 100% of the original starlight, and it's only dropped to about 99%. Given that planets tend to be quite a bit smaller than stars, you don't expect a planet to block out a lot of the light. 0.5%, 1%, 1.5% is actually quite a big planet to block light from a distant star. But with something like the James Webb Space Telescope staring at a distant star, you can get enough data to clearly see the dips and start to work out what type of planet has actually passed in front of the distant star. Number 3 is taking a disk and blocking out the starlight. So that planet was there all the while, but it's difficult to see when you have a really, really bright star next to it. It makes it almost impossible because of the amount of light that would be scattered in your telescope. It makes it almost impossible to see any planets that might be going around this star. This star looks a bit ragged just because it's a snapshot of what you would expect to see when individual photons come from a very distant star. But again, if we actually do that animation one more time and actually block the light from the star, then it might be possible to then see much fainter planets that are very close by. And again, this has been done by a number of different telescopes. So here, a time lapse taken over many, many years where the central star has been blocked, and now we see these faint blobs, all of which are moving around the central star. The closest one is moving quite quickly, the furthest ones appear to be moving more slowly, just like we would expect if we were looking down on Mercury, Venus, Earth, Mars, etc. in our solar system. The inner planets would be moving quite quickly and the outer planets would be moving quite slowly. So this is a time lapse taken over quite a few years. And here's another one where this time the planetary system is edge on. So again, we're blocking out the star, but when the planet is far enough away from the star, then it's possible to see it as a little blob. Too close to the star, we don't see it, but when it's far enough away from the star, it's possible to see a clear planet. And again, this is a time lapse taken over a long period of time, so these planets are probably quite a long way from their star. It's very difficult to find planets that are very close to a star, but given enough patience and enough years of data, it's possible to actually directly image planets going around other stars. This idea of taking a small occulting disk and blocking out the starlight has been used a number of different times. In the James Webb Space Telescope, a rather bright star in the middle there has been blocked out with an occulting disk, and then with a long exposure, which would have been impossible if the star was still there, but a long exposure now shows that this star is actually surrounded by a huge disk of debris, dust and debris. And we think this is a planet formation disk. In other words, this is perhaps what our solar system might have looked like in the very early days of our solar system, something I'll be coming back to in the next talk. So this doesn't appear to be a disk full of planets. It appears to be a disk with different structures, a bit like if you were to look at the dust and the debris in our solar system. We have an asteroid belt, for instance, and then we have some planets. And beyond Neptune, we have a Kuiper belt, another belt of a huge number of icy objects. Perhaps what we're looking at is something similar to an asteroid belt or a Kuiper belt in another solar system. But with the resolution we have from the James Webb Space Telescope, it doesn't seem to be possible in this solar system to actually see individual planets. Maybe because they're not big enough or bright enough, maybe because they haven't formed yet. We have to think about how old the stars are and how long the planets have had in their formation. So this is a star called Fomalhaut. It's one in the constellation of the Southern Fish. So let's have a think about what we can learn about exoplanets. I said the wobble technique, whereby we can use the mass of a planet to make the star wobble, which then moves backwards and forwards, and we can see that by looking at the colors of the star, the spectrum of the star. So we can get the mass of a star from the wobble, and we can get the size of a star if it transits. If we're lucky enough to find a solar system where we can use both techniques, then if we can use radial velocity and transits, then we can get information about the mass from the radial velocity, the wobble, and we can get the size from the transits. So if we can apply both techniques, and it does depend on the solar system being at the right angle so that we can get a transit. If we're looking down on the top of a solar system, none of the planets will pass in front of the star, so that doesn't work. We have to be lucky enough to have the right alignment of the solar system. But if we can get the mass and the size, then with both of those bits of information, we can get an estimate of the density of the planet. If the mass and size tell us that the density is very high, then it's probably a rocky planet. If the mass and the size tell us that the density is very low, then it's more likely to be a gas planet, a gas giant perhaps. Using spectroscopy, we can get an idea of what the atmosphere is made of, whether it has an atmosphere and what molecules are present in the atmosphere. With the density, we can get an idea of the type, rocky, gaseous, etc. Spectroscopy will tell us if we're dealing with a rocky planet, does it have an atmosphere? And if we're dealing with a gas planet, perhaps what it's made of. We can also get an estimate of the temperature. And it is only an estimate, but it's a reasonable estimate. If we know what the star is, and we're fairly good at figuring out what type of star we're looking at. If we look at the color of the star, if we look at the spectrum of the star, we can figure out, is this a star like our sun? Or is it a red dwarf, or is it a giant, etc. We can get an idea of the mass and the size of the star we're dealing with. And if we know how long it takes the planet to go around that star, we can figure out how far it is away, because we know about Newton's law of universal gravity. The gravity of an exoplanet, gravity is the same as the gravity here in our solar system. There's no difference in the physics. So if we know how massive the star is and we know how long it takes the planet to go around the star, we can figure out how close it is to the star. And if we know about the luminosity of the star, then we can figure out how warm that planet is. Is it close enough that that planet is really hot? Or is it far enough away that that planet is probably very cold? We can estimate the temperature, and that will give us a good guide as to whether we're talking about an ice planet or a water planet or a lava planet, perhaps. The temperature range can be extreme. But if we can piece together enough bits of information, we can learn a surprisingly large amount about a planet, even if we're not even capable of seeing it. From this various set of techniques, by looking at the light from the star, either its spectrum or its intensity, we can learn quite a lot about the planet, even if we can't directly image it. And that means that we've now found lots of exoplanets. We've been looking for quite a few decades now. The first exoplanet was discovered in the 1990s, and a huge number of exoplanets have been found in the last couple of decades. This is not all of them. This is just a small selection of some of the exoplanets that have been found, and they're put into this sort of zoo, if you like. The vertical scale means nothing in particular. They're all approximately to scale, as judged by the best guess we've got of their sizes. But they are arranged in terms of temperature. Cold planets on the left and hot planets on the right. But the vertical position doesn't mean anything in particular. So there is a temperature scale there. Any planet on the extreme left-hand side would have an equilibrium temperature. In other words, a temperature regardless of whether it's got an atmosphere or not, way down in the sort of -200s or so. Any planet over on the right-hand side would have temperatures in excess of +200 Celsius. So we're not talking about water on any of the planets over on the extreme right. Just to get a sort of sense of where we are, although this is called exoplanets, there's actually our own solar system planets are interloping in here. So down in the bottom left-hand corner, I've just blown it up there, we can see Jupiter and Saturn and Uranus and Neptune, just as a reminder of how large they are in terms of these other planets. So some other planets are larger than Jupiter. Some of the planets we've found are only the size of Earth. But if we were interested in finding life, well, we don't necessarily need water for life, but it really makes it a lot easier. We know that if you start with water and you start with an energy source like the star, and you have enough of the right molecules and compounds, then it looks like life can find a way. It would be nice to prove that's the case by going somewhere else where we know there's water, like the icy moons of Jupiter, for instance. If we find water there, is it possible we find life there? Possible. We don't need water, but it seems like a good place to start. So of all the planets that we've seen, how many of them are in the right place in terms of the distance to their star such that liquid water might exist? If we're way over to the left, we're probably in an icy planet. If we're way over to the right, then basically it's impossible for water to exist because it would have turned to vapor. There is an ideal position between those extremes, but unfortunately, the Goldilocks zone, where that's just right for water to exist, is relatively narrow. In other words, everything blanked out there is too cold for water to exist. Everything will just be ice, and everything on the right-hand side there, basically, it would turn to vapor. There's only a relatively narrow strip in temperature in terms of, for any given star, how far away from the star do you have to be for liquid water to exist? And just to give you, again, a sense of scale, as it were, if we put our own planets in there, Mars is too far away from the sun to have flowing water at the moment, maybe not in the past, but at the moment it hasn't got flowing water. And if we think of Venus, well, that's far too hot, with a surface temperature of many hundreds of degrees. And no surprise, Earth is right in the middle of the Goldilocks zone. Not too warm, not too cold, but just right for liquid water as well as ice and water vapor to exist, which gives us this situation where life flourished. If we are going to be looking for life, maybe we ought to concentrate in this strip there. Other people say, no, we shouldn't necessarily concentrate only on those planets. It's possible for life to exist under other circumstances where liquid water doesn't necessarily exist on the surface of the planet. So people differ as to the best place to look, but that does seem to be a reasonable place to start. Let's have a think about some of these exoplanets that have been found. This particular graphic shows about 1,000 of them, and I think the current total is about 6,000. Surprisingly, or at least I thought it was rather surprising, we found that our immediate neighbor, Proxima Centauri, our immediate Alpha Centauri neighbor, has got a star called Proxima Centauri that has planets. A few decades ago, we weren't sure how many stars had planets. The fact that we find our immediate neighbor has got planets makes it sound like, well, they must be really common, or is it just a fluke that the closest neighbor we've looked at happens to have a solar system with planets going around it? It seemed remarkable. I didn't really think that we'd be so lucky as to find a planetary system only 4 light years away from us, compared to the hundreds or thousands of light years of some of these other planetary systems. One of the oldest is this one that's been nicknamed Methuselah. This planet appears to be about 12.7, it says here, 12.7 billion years old. Remember, the universe is only about 13.7, 13.8. So this planet apparently came into existence very early on in the universe. We know of no way that a star can be born and then give rise to planets later. I'll be again talking about the origins of solar systems in the next talk. But it looks like if the star is old, then the planet must be old as well, because we know of no way that a planet can be born by a middle-aged star. Basically, planets and stars are born at the same time. So it looks like this star produced a planet 12.7 billion years ago. So it looks like the universe started making planets almost as soon as it could, which makes us think that, yes, again, there are an awful lot of planets out there. We've only found thousands of them, but we haven't looked at every star to see if it's got a solar system. Statistically, it looks like a very large fraction of stars will have planets going around them. If we have a look in the top right there, remember the right-hand side are very hot planets. This one has a surface temperature of thousands of Kelvin. So that's not the sort of place you probably want to visit. This is very close to its host star compared to the ones over here on the left-hand side. And the one in the bottom right, it looks like a bit of distortion there, but no, that is the actual shape of this planet, we believe. It's difficult to be precise, but this planet is so close to its parent star that it is thought that the parent star is basically producing tides on this planet, which is pulling the planet out into an egg shape. Simply because of its proximity, it is only a few million kilometers. Remember, we are 150 million kilometers from our star. This one is closer by more than 1, approaching 2 orders of magnitude. So it is very hot and so close it's getting stretched into an egg shape. So we don't really think those are places which could harbor life, but they're interesting in their own right as the extremes of what planets can be. There are various other interesting planets in this particular set. There's one there that's very large. Perhaps you can see it on the right-hand side there. That goes under the wonderful name of HATP67b. Astronomers really need to get their act together with naming these things. But if there are 6,000 of them, you can understand that they find it difficult. This planet appears to be huge. It's something like 10 times the size of our Jupiter, and yet it's less massive than our Jupiter. So if it's that much bigger but not as massive, it must be a really low density planet. It is thought that the average density of that particular planet is something like marshmallow, something like that. It is by no means anything close to the rocky planet that we know and love under our feet, and not even the same as our neighbor Jupiter. But of course, we are getting ridiculous names here. I did wonder whether or not these astronomers or astrophysicists ought to get their act together and start naming these planets a little better. And then I realized that somebody did come up with a fantastic name, and that is Coconuts 2b. I think they reverse engineered that. They said, let's think of a name. Coconuts, that sounds ridiculous. What do we call it? Oh yeah, Cool Companions on Ultra-Wide Orbits, reverse engineering the acronym to get something useful. That means objects that are an awful long way from their star. Ultra-wide orbits just literally means their orbits are huge and the planet spends most of its time a huge distance away from its star. The distance from the Earth to the Sun is 1 astronomical unit. This object is something like 7,500 astronomical units from its host star. So it's more distant from its star by a factor of 7,500 compared to we are from our Sun. We take 1 year to go around our Sun. It takes, estimated, maybe 1 million years to go round its star once. And that's by no means the weirdest one on this particular exoplanet zoo. I think the winner of the weirdest one has to be this one down here, LHS 1140b, which I'm sure you all know, yes. This little tiny one there. We think, based on all of the calculations that can be done, it's an ice planet. It's an ice planet based on its distance from the Sun and how much light is coming from the Sun, how much energy is coming from the Sun. It's an ice planet, but it's close enough to its star. It's icy, but it's close to its star simply because the star isn't very luminous, so it has to be fairly close to the star. It's an ice planet, but it is tidally locked to the star, which means it always faces, one face of the planet is always facing the star, unlike Earth, which rotates once in 24 hours as it does its 365-day journey around the Sun. This planet, 1 day is the same as 1 year, so it always faces the star, which means one side of the planet is always facing the star and getting warm. So even though it's an ice planet, it's thought that maybe it's an ice planet with a little bit of a thaw on the side that's facing the Sun. In other words, is it actually a global ice sheet, but with an ocean in the bit that's actually facing the star? So you end up with something that looks rather creepily like an eyeball. Now, that is conjecture, but that's based on what we know about its temperature, its likely temperature, its distance from the star, whether it's likely to be tidally locked, etc. This is all based on the physics we understand from the techniques we've used and our understanding of gravity. So whether or not that does turn out to be an ice ball planet and whether there's any more like that, we don't know. But in the last few years, we have found 6,000 exoplanets, some of which appear a little bit like Earth and others that appear to look rather different. What spacecraft, we know about the techniques, what particular spacecraft have been used to find these exoplanets? Well, some of them have been studied by these space telescopes, Gaia in the top left and the James Webb Space Telescope in the bottom right there. These particular space telescopes are not designed to find exoplanets. Gaia is designed to simply map where the stars are so that we have a better understanding of the Milky Way. But by mapping accurately the positions of stars, it's found that some stars appear to wobble or move in small circles, which indicates that there's a massive planet going around them. In some cases, it finds that the stars themselves are binary stars and there are two stars orbiting each other. But in some cases, it can quite distinctly see a star which appears to be moving in a circle and it can't see anything else. And we deduce that it's got planets going around it. So Gaia Space Telescope has found some exoplanets. James Webb Space Telescope doesn't tend to find planets. Its job is too important. It's got too little time to study all the things that we want to study. So it's told to go and look in more detail at objects that we already know have exoplanets, like the one I showed you earlier, where it's now seen this dusty disk surrounding the star where planets are forming. So in other words, when satellites or space telescopes find exoplanets, the James Webb Space Telescope might be told, go and have a closer look at this particular system. And these are the various telescopes, some on Earth, but mainly in space, that have been looking for exoplanets in the past. Kepler has done a wonderful job and found thousands of exoplanets via the transit method, but you can see that in the near future we'll be having more coming online. The European Space Agency is going to be launching one in another year or so called Plato. And assuming a certain somebody doesn't cancel it, there will be a NASA mission in 2027 called the Nancy Grace Roman, or Roman for short, telescope, which will be launched, and a long way into the future, there might be a possibility of an HWO, a Habitable Worlds Observatory. In other words, a space telescope explicitly looking to study other Earths, but that won't be launched for many a year just yet. I said earlier that one way of directly imaging a star is to use an occulting disk, usually a very small disk, not one this size, a tiny little disk inside the telescope to block the light of the star. But with the Nancy Grace Roman, they thought, well, there actually might be another way of doing it. And so there are plans, though nothing is set in stone just yet, there are plans to launch the Roman telescope with a star shade. That's a star shade which detaches from the telescope and then unfurls itself to produce not a tiny little disk, but an absolutely huge disk about 100 meters in diameter, which is then flown 50,000 kilometers away and blocks the star from a huge distance. So it needs the choreography of the space telescope and the star shade, and if the star shade covers the star, then hopefully it'll block the light of the star and allow us to see planets orbiting around that star. So it'll only be used for stars where we have a good reason to believe that there is a solar system there. And it's going to be a big technical challenge to fly an object that distance away and line it up as close to perfect as possible, and then station keep those two to make sure that the disk, the star shade, stays in front of the star. But it has the advantage that the starlight never gets into the telescope, whereas the idea of blocking the starlight once it's in the telescope has the problem that once the starlight is in, it gets scattered, and if it's 1,000,000 times brighter than the planet, even a tiny amount of scattered light could mean that you don't see the planets. So this is scientifically better, but a bigger technological challenge. I said it would be nice to look for life. How do we look for life when we're looking at planets? Well, one option is to look at planets that are transiting. A planet might move in front of the star or behind the star. If you look at the spectrum from the combined two, again, you might not be able to see the planet, but if you look at the spectrum from the two of them, when the planet goes behind the star, you lose any light from the planet, and so the spectrum would presumably change. Also, when the planet is going in front of the star, if it's got an atmosphere, some of the starlight will be going through the atmosphere and then coming to Earth. So if you look for the depth of the dip here, remember that depends on how big the planet is, for some molecules at some wavelengths corresponding to some molecules, the planet will look a little bit bigger because it's got an atmosphere, which makes it look a little bit bigger than if the wavelength is chosen so that it doesn't get absorbed by the atmosphere, the planet will appear to be smaller. So the depth you get will depend on the wavelength, and the wavelength will tell you about the molecules that are in the atmosphere. So again, James Webb Space Telescope has done this. The light from the star is fixed and there it dips, but down here, we've blown it up at the bottom there, we have red dots corresponding to one wavelength and blue dots corresponding to a different wavelength and yellow dots corresponding to a different wavelength. There's a different depth to the dip, implying that at different wavelengths, the planet appears to be a slightly different size, indicating that it has an atmosphere which absorbs light at some wavelengths, but not at other wavelengths. If we choose the wavelengths carefully, we can actually tell, does this atmosphere contain carbon dioxide? Does it contain water? Does it contain methane? Does it contain anything else? James Webb has done this and has determined that certain planets contain certain elements such as sodium or water or carbon monoxide or carbon dioxide. And each of these peaks here in the spectrum indicates that the starlight has dipped by a certain amount, and that tells us about the molecules that are in the atmosphere. If we do this with a number of different planets, we may see molecules in the atmosphere indicating that life exists. For instance, do we see oxygen, which would come from life converting CO2 into oxygen? Let me just finish, because I'm running out of time here. Let me finish by giving you an indication of what planets have been found. Here, plotting them, a dot for each planet that's been found. The dot is positioned according to its mass on this scale compared to our Jupiter as a reference, and on the horizontal scale, how long it takes to go around its star. There's our planets in our solar system just for reference. So as the dates click by, there's the date in the top left-hand corner, as the date clicks by over the last 2 decades or so, you can see more and more planets have been found. Different techniques have been used, originally the wobble technique, then the transit technique, because Kepler produced a huge number of new planets. And you can see that if we come up to the present day, or I think this finishes at 2024, you can see that we've got thousands upon thousands of planets that span all the way from those that are much heavier than Jupiter to those that are relatively lightweight, those that are very close to their host star and those that are a very long way away. You might say, well, doesn't this prove that all solar systems are different to ours? Because there's our planets and they all appear to be at the bottom of this huge scatter of points here. That doesn't mean solar systems out there are different from our solar system. It simply means that big planets are easier to find. It simply means that planets closer to their sun are easier to find if they produce a certain amount of wobble of the star. So just because we don't find many planets around here where Earth is sitting, that doesn't mean they're not out there. We have to take into account this bias that some planets are easier to find than others. And it turns out Earths are not easy to find. Jupiter's dead easy, 10 a penny, easy to find Jupiters around other planets. Earth's altogether more tricky because they are smaller and lighter. So they don't have the same wobble, they don't have the same dip in the light curve. So if you're interested in exoplanets, NASA have catalogued them all. All 6,000 exoplanets, you can go and look up where they are, what color they are, what size they are, what mass they are, whether they have an atmosphere or not, etc. All of this information is documented in these web pages. Don't bother making a note, they're in the handouts here. And if you are interested in what's coming up in the very near future, the next few years will be quite interesting because both the European Space Agency and NASA are going to be launching new telescopes which should be even more accurate and should find even more exoplanets and tell us more about what's out there and whether there's the possibility of life out there. Watch this space. Thank you very much.